of Earth depends largely on the total radiation received from the Sun. The Earth reflects about 30% of the solar energy radiation reaching it and absorbs the remaining 70%. The absorbed solar radiation heats up the Earth. While the Earth continually absorbs solar radiation, it will not simply continue to heat up. In response to this heating, the Earth emits long-wave radiation into space. The emission of long-wave radiation cools the Earth. As the Earth cools, it emits less radiation to space, but because it is still continually absorbing solar radiation, it still heats up. As it heats up, the Earth emits more radiation to space, and so it cools. This dynamic physical process of absorption and emission and resultant heating and cooling creates what is known as a state of equilibrium. The term equilibrium describes a stable condition where all of the influencing factors are in balance and so cancel each other out. Because of this equilibrium, the temperature of the Earth has been relatively constant over time. For scientists, this balance between the amount of solar radiation absorbed and the amount of long-wave radiation emitted by the Earth is known as radiative equilibrium. Radiative equilibrium tells us that the long-wave radiation emitted by the Earth will equal the amount of solar radiation that is absorbed by the Earth. In fact, we can determine the temperature of the Earth by knowing the amount of long-wave radiation it emits. If one of the components of the Earth's energy balance changes the amount of long-wave radiation the Earth emits, the temperature of the Earth will also change, and the Earth will arrive at a new radiative equilibrium. For example, if the amount of solar radiation absorbed were to suddenly increase, the amount of long-wave radiation emitted would also increase. The temperature of the Earth would then increase, but a new radiative equilibrium would be reached, so the Earth would not continue to become hotter. In summary, the Earth's radiative equilibrium describes the balance between the incoming shortwave and the outgoing long-wave radiation. The temperature of the Earth can be determined by the amount of outgoing long-wave radiation, which is equal to the amount of incoming solar radiation absorbed by the Earth.
Remember that white light from the sun is made up of all the wavelengths of colors in the visible spectrum. When we point the probe at the sun, the spectrophotometer shows full intensity of all wavelengths in the visible spectrum. You may also expect a white light bulb to emit all the colors in the visible spectrum. However, when we use the spectrophotometer, it shows that some wavelengths are not emitted as much as others. Here is that red ornament under sunlight. Now it is easier to see that the ornament does reflect red wavelengths of light. Compare how the ornament's reflected light is different under the white light bulb than when it is under the sun. This illustrates how the properties of light are not always consistent with what we see. Another example is when we mix colors of light on the surface of a table. The combined emissions from a green bulb and a red bulb look yellow. However, the probe does not show that yellow wavelengths of light are present. So why do we see yellow? You are probably familiar with how paint combines to form additional colors. The primary colors of red, yellow, and blue can be combined to create other colors, such as orange, green, and purple. This is called a subtractive model. However, when we mix light, it follows an additive model. The additive model is also called the RGB model because when we combine the primary light colors of red, green, and blue, it produces additional colors such as magenta, cyan, and yellow. We can use the RGB model to explain why combining red and green light appears yellow. You also investigated how light is transmitted through colored water. The spectrophotometer shines white light through the cuvette and measures the absorbance and transmission of the light when it passes through the liquid. You probably expected the yellow wavelengths to be transmitted, but with your knowledge of the RGB model, you should also understand why green and red wavelengths are also transmitted. What wavelengths are absorbed by the yellow water? Transmittance and absorbance have an inverse or opposite relationship. So the wavelengths that are absorbed are those that are not transmitted. In this case, blue and violet are absorbed.